Definition of orthogonal projection. Suppose U and V are vectors in inner product space like V. Suppose vector V is non-zero. Then the orthogonal projection of U onto V is defined as the inner product of UV divided by inner product of V by itself multiplied by vector V. So, example for you, use Euclidean inner product in the space to find the orthogonal projection of U onto V. So let's begin. When we're talking about Euclidean inner product in the space, we're basically referring to the dot product between vectors. So U dot V is 1 times 6 plus 2 times 2 plus 0 times 4, which is 10. The dot product between V and itself is 1 times 1 plus 2 times 2 plus 0 times 0, which is 5. So you can basically find that the orthogonal projection of U onto V as 10 divided by 5 multiplied by vector V, which is 1, 2, 0. So you have 2 times 1, 2, 0, which is 2, 4, and 0. You can take a look at the graph as well. So if you consider vector U for 6, 2, and 4, and consider vector V, which is 1, 2, and 0, then the orthogonal projection of U over V is going to be the vector 2, 4, and 0, which is in the direction of vector V. So you found a scalar multiplied by vector V. Pay attention here. This is a scalar that you found, and then you multiply that by vector V. And that is basically the orthogonal projection of U onto V. We have a nice theorem. The theorem says, suppose U and V are two vectors in an inner product space V, and suppose V is non-zero vector. Then the distance between U and the projection of U onto V is less than the distance between U and CV. Very good. Let's take a look at the sketch of the proof. Consider B to be this scalar, the inner product between U and V divided by the inner product between V and V. Now, if you find the magnitude of U minus CV to the second power, it is equal to the inner product between U minus CV by itself. Or basically, you're finding the magnitude of U minus BV plus B minus CV. So basically, if you just do the distribution here, you can see that you have U minus BV plus BV minus CV. So we're just adding and subtracting BV here. But we need that because eventually we're going to separate these. U minus BV and B minus CV are orthogonal. You can check that. You can find the inner product between these two and show that it is equal to 0. It's not that difficult. But remember that from Pythagorean theorem, we know that the magnitude of U minus BV plus B minus C times V to the second is equal to U minus BV to the second plus the magnitude of B minus C V to the second. This is the Pythagorean theorem. As long as you have orthogonal vectors, you can just simplify this as follows. U plus V to the second, or the magnitude of U plus V to the second is equal to magnitude of U to the second plus magnitude of V to the second. Now, this implies that the magnitude of U minus CV to the second, which is this quantity here on the left-hand side, is equal to the magnitude of u minus bv to the second plus b minus c to the second times magnitude of v to the second. Well, since b is not equal to c and v is non-zero, for sure you can say that b minus c to the second times the magnitude of v to the second greater than 0. This means that the magnitude of u minus bv to the second must be less than the magnitude of u minus cv to the second. But what's the meaning of that? If you take the square root of both sides, it means that the distance between u and bv is less than the distance between u and cv. So we just prove this nice theorem. Perfect. Example for you. Find an orthogonal projection in the vector space of all continuous functions over closed interval a and b with inner product given to you as definite integral between a and b of multiplication of two functions. So f is function 1, g is function x, and this is your vector space. You already have the inner product function. We already proved this is an inner product. Find the orthogonal projection of f onto g. Very good. Remember the definition of orthogonal projection. The orthogonal projection of u onto v is equal to the inner product of uv divided by inner product v and v in the direction of vector v. But again, this is, guys, just a scalar. This is just a number multiplied by vector v. Let us begin. What's the inner product between f and g? It is definite integral 0 to 1 f times g, which is the definite integral 0 to 1 of 1 times x, which is just x. It is going to be a half x squared between 0 and 1, which is just a half. So basically, you found your numerator. The numerator is a half. The denominator should be very easy for you to calculate. For the denominator, you just have the inner product between g and g. The orthogonal projection of f onto g is a half divided by a third. A third is just the inner product between g and g, which is definite integral 0 to 1. G is function x. X times x gives you x squared. Dx, we just proved this in previous example, which is going to be a third x cubed or just a third. This should be easy for you to calculate. We're going back to calculus. So this goes on the denominator. A half divided by a third times x. X is your function g or vector v, which gives you 3/2 x. So the orthogonal projection of constant function 1 onto linear function x is a linear function 3/2 x. You're just changing the slope. The slope of g was 1. Now the slope is 3/2, everybody. That's how you find the orthogonal projection of a function, which is a vector, onto another function, which is another vector in this vector space.